Good morning, good evening, and good afternoon, everyone. Welcome to this MapReduce tutorial where we will learn about MapReduce, how it works, what is MapReduce, and what are the benefits of using MapReduce. So, MapReduce is basically a programming model, or you could also say it's a processing framework, although for processing framework, yarn would be the right word to use, and MapReduce is a programming model. So we'll understand about MapReduce analogy. What is Hadoop MapReduce? What do you mean by parallel processing in MapReduce? Hadoop MapReduce workflow, and then finally we would have a demo on MapReduce. Now, suppose you have a library that has a collection of huge number of books on each floor, and you want to count the total number of books present on each floor. What would be your approach? You could say, I will do it myself, but then don't you think that will take a lot of time? And that's obviously not an efficient way of counting the number of books in this huge collection on every floor by yourself. Now, there could be a different approach or an alternative to that. You could think of asking three of your friends or three of your colleagues, and you could then say if each friend could count the books on every floor, then obviously that would make your work faster and easier to count the books on every floor. Now, this is what we mean by parallel processing. So when you say parallel processing in technical terms, you're talking about using multiple machines, and each machine would be contributing its RAM and CPU cores for processing, and your data would be processed on multiple machines at the same time. Now, this type of process involves parallel processing in our case, or in our library example, where you would have person 1 who would be taking care of books on floor 1 and counting them, person 2 on floor 2, then you have someone on floor 3 and someone on floor 4. So every individual would be counting the books on every floor in parallel, so that reduces the time consumed for this activity. And then there should be some mechanism where all these counts from every floor can be aggregated. So what is each person doing here? Each person is mapping the data of a particular floor, or you can say each person is doing a kind of activity or basically a task on every floor, and the task is counting the books on every floor. Now then you could have some aggregation mechanism that could basically reduce or summarize this total count, and in terms of MapReduce we would say that's the work of reducer. So when you talk about Hadoop MapReduce, it processes data on different node machines. Now this is the whole concept of Hadoop framework, right? That you not only have your data stored across machines, but you would also want to process the data locally. So instead of transferring the data from one machine to other machine, or bringing all the data together into some central processing unit and then processing it, you would rather have the data processed on the machines wherever that is stored. So we know in case of Hadoop cluster, we would have our data stored on multiple data nodes on their multiple disks, and that is the data which needs to be processed. But the requirement is that we want to process this data as fast as possible, and that could be achieved by using parallel processing. Now, in case of MapReduce, we basically have the first phase, which is your mapping phase. So in case of MapReduce programming model, you basically have two phases. One is mapping and one is reducing. Now, who takes care of things in mapping phase? It is a mapper class. And this mapper class has the function which is provided by the developer, which takes care of these individual map tasks which will work on multiple nodes in parallel. Your reducer class belongs to the reducing phase. So a reducing phase basically uses a reducer class which provides a function that will aggregate and reduce the output of different data nodes to generate the final output. Now that's how your MapReduce works, using mapping and then obviously reducing. Now you could have some other kind of jobs which are map only jobs, wherein there is no reducing required. But we are not talking about those. We are talking about our requirement where we would want to process the data using mapping and reducing, especially when data is huge, when data is stored across multiple machines, and you would want to process the data in parallel. So when you talk about MapReduce, you could say it's a programming model. You could say internally it's a processing engine of Hadoop that allows you to process and compute huge volumes of data. And when we say huge volumes of data, we can talk about terabytes, we can talk about petabytes, exabytes, and that amount of data which needs to be processed on a huge cluster. We could also use MapReduce programming model and run a MapReduce algorithm in a local mode. But what does that mean? If you would go for a local mode, it basically means it would do all the mapping and reducing on the same node using the processing capacity, that is RAM and CPU cores, on the same machine, which is not really efficient. In fact, we would want to have our MapReduce work on multiple nodes, which would obviously have mapping phase followed by a reducing phase, and intermittently there would be data generated. There would be different other phases which help this whole processing. So when you talk about Hadoop MapReduce, you are mainly talking about two main components or two main phases, that is mapping and reducing. Mapping taking care of map tasks, reducing taking care of reduced tasks. So you would have your data which would be stored on multiple machines. Now when we talk about data, data could be in different formats. We could, or the developer could specify what is the format which needs to be used to understand the data which is coming in. That data then goes through the mapping. Internally there would be some shuffling, sorting, and then reducing, which gives you your final output. So the way we access data from SDFS, or the way our data is getting stored on SDFS, we have our input data which would have one or multiple files and one or multiple directories, and your final output is also stored on SDFS to be accessed, to be looked into, and to see if the processing was done correctly. So this is how it looks. So you have the input data which would then be worked upon by multiple map tasks. Now how many map tasks? That basically depends on the file. That depends on the input format. So normally we know that in a Hadoop cluster you would have a file which is broken down into blocks depending on its size. So the default block size is 128 MB, which can then still be customized based on your average size of data which is getting stored on the cluster. So if I have really huge files which are getting stored on the cluster, I would certainly set a higher block size so that my every file does not have huge number of blocks creating a load on name nodes RAM, because that's tracking the number of elements in your cluster or number of objects in your cluster. So depending on your file size, your file would be split into multiple chunks, and for every chunk we would have a map task running. Now what is this map task doing? That is specified within the mapper class. So within the mapper class you have the mapper function which basically says what each of these map tasks has to do on each of the chunks which has to be processed. This data intermittently is written to SDFS where it is sorted and shuffled, and then you have internal phases such as partitioner which decides how many reduce tasks would be used or what data goes to which reducer. You could also have a combiner phase which is like a mini reducer doing the same reduce operation before it reaches reduce. Then you have your reducing phase which is taken care by a reducer class, and internally the reducer function provided by developer which would have reduce task running on the data which comes as an output from map tasks. Finally, your output is then generated which is stored on SDFS. Now in case of Hadoop, it accepts data in different formats. Your data could be in compressed format, your data could be in Parquet, your data could be in Avro, text, CSV, TSV, binary format, and all of these formats are supported. However, remember, if you're talking about data being compressed, then you have to also look into what kind of splittability the compression mechanism supports. Otherwise, when MapReduce processing happens, it would take the complete file as one chunk to be processed. So SDFS accepts input data in different formats. This data is stored in SDFS, and that is basically our input, which is then passing through the mapping phase. Now what is mapping phase doing? As I said, it reads record by record. Depending on the input format, it reads the data. So we have multiple map tasks threads running on multiple chunks. Once this data is being read, this is broken down into individual elements. And when I say individual element, I could say this is my list of key value pairs. So your records based on some kind of delimiter or without delimiter are broken down into individual elements, and thus your map creates key value pairs. Now these key value pairs are not my final output. These key value pairs are basically a list of elements which will then be subjected to further processing. So you would have internally shuffling and sorting of data so that all the relevant key value pairs are brought together, which basically benefits the processing. And then you have your reducing, which aggregates the key value pairs into set of smaller tuples or tuples, as you would say. Finally, your output is getting stored in the designated directory as a list of aggregated key value pairs, which gives you your output. So when we talk about MapReduce, one of the key factors here is the parallel processing which it can offer. So we know that our data is getting stored across multiple data nodes, and you would have huge volume of data which is split and randomly distributed across data nodes, and this is the data which needs to be processed. And the best way would be parallel processing. So you could have your data getting stored on multiple data nodes or multiple slave nodes, and each slave node would have again one or multiple disks. To process this data, basically we have to go for parallel processing approach. We have to use the MapReduce. Now let's look at the MapReduce workflow to understand how it works. So basically you have your input data stored on SDFS. Now this is the data which needs to be processed. It is stored in input files, and the processing which you want can be done on one single file, or it can be done on a directory which has multiple files. You could also later have multiple outputs merged, which we achieve by using something called as chaining of mappers. So here you have your data getting stored on SDFS. Now input format is basically something to define the input specification and how the input files will be split. So there are various input formats. Now we can search for that. So we can go to Google and we can basically search for Hadoop MapReduce Yahoo tutorial. This is one of the good links. And if I look into this link, I can search for different input formats and output formats. So let's search for input format. So when we talk about input format, you basically have something to define how input files are split. So input files are split up and read based on what input format is specified. So this is a class that provides following functionality. It selects the files or other objects that should be used for input. It defines the input split that break a file into tasks, provides a factory for record reader objects that read the file. So there are different formats if you look in the table here, and you can see that the text input format is the default format, which reads lines of a text file, and each line is considered as a record. Here the key is the byte offset of the line, and the value is the line content itself. You can have key value input format, which parses lines into key value pairs. Everything up to the first tab character is the key, and the remainder is the line. You could also have sequence file input format, which basically works on binary format. So you have input format, and in the same way you can also search for output format, which takes care of how the data is handled after the processing is done. So the key value pairs provided to this output collector are then written to output files. The way they are written is governed by output format. So it functions pretty much like input format as described in earlier, right? So we could set what is the output format to be followed, and again you have text output, sequence file output format, null output format, and so on. So these are different classes which take care of how your data is handled when it is being read for processing, or how is the data being written when the processing is done. So based on the input format, the file is broken down into splits, and this logically represents the data to be processed by individual map tasks. or you could say individual mapper functions. So you could have one or multiple splits which need to be processed depending on the file size, depending on what properties have been set. Now once this is done, you have your input splits which are subjected to mapping phase. Internally you have a record reader which communicates with the input split and converts the data into key value pairs suitable to be read by mapper. And what is mapper doing? It is basically working on these key value pairs, the map task, giving you an intermittent output which would then be forwarded for further processing. Now once that is done and we have these key value pairs which is being worked upon by map, your map tasks as a part of your mapper function are generating your key value pairs which are your intermediate outputs to be processed further. Now you could have, as I said, a combiner phase or internally a mini reducer phase. Now combiner does not have its own class. So combiner basically uses the same class as the reducer class provided by the developer, and its main work is to do the reducing, or its main work is to do some kind of mini aggregation on the key value pairs which were generated by map. So once the data is coming in from the combiner, then we have internally a partitioner phase which decides how outputs from combiners are sent to the reducers. Or you could also say that even if I did not have a combiner, partitioner would decide based on the keys and values, based on the type of keys, how many reducers would be required or how many reduce tasks would be required to work on your output which was generated by map task. Now once partitioner has decided that, then your data would be then sorted and shuffled, which is then fed into the reducer. So when you talk about your reducer, it would basically have one or multiple reduce tasks. Now that depends on what partitioner decided or determined for your data to be processed. It can also depend on the configuration properties which have been set to decide how many reduce tasks should be used. Now internally all this data is obviously going through sorting and shuffling so that your reducing or aggregation becomes an easier task. Once we have this done, we basically have the reducer, which is the code for the reducer is provided by the developer, and all the intermediate data has then to be aggregated to give you a final output, which would then be stored on SDFS. And who does this? You have an internal record writer which writes these output key value pairs from reducer to the output files. Now this is how your MapReduce works, wherein the final output data can be not only stored but then read or accessed from SDFS or even used as an input for further MapReduce kind of processing. So this is how it overall looks. So you basically have your data stored on SDFS. Based on input format, you have the splits, then you have record reader which gives your data to the mapping phase, which is then taken care by your mapper function. And mapper function basically means one or multiple map tasks working on your chunks of data. You could have a combiner phase which is optional, which is not mandatory. Then you have a partitioner phase which decides on how many reduce tasks or how many reducers would be used to work on your data. Internally there is sorting and shuffling of data happening, and then basically based on your output format, your record reader will write the output to SDFS directory. Now internally you could also remember that data is being processed locally, so you would have the output of each task which is being worked upon stored locally. However, we do not access the data directly from data nodes, we access it from SDFS, so our output is stored on SDFS. So that is your MapReduce workflow. When you talk about MapReduce architecture, now this is how it would look. So you would have basically a edge node or a client program or an API which intends to process some data. So it submits the job to the job tracker, or you can say resource manager in case of Hadoop Yarn framework, right? Now before this step, we can also say that an interaction with name node would have already happened, which would have given information of data nodes which have the relevant data stored. Then your master processor. So in Hadoop version 1 we had job tracker, and then the slaves were called task trackers. In Hadoop version 2, instead of job tracker you have resource manager, and instead of task trackers you have node managers. So basically your resource manager has to assign the job to the task trackers or node managers. So your node managers as we discussed in Yarn, are basically taking care of processing which happens on every node. So internally there is all of this work happening by resource manager, node managers, and application master, and you can refer to the Yarn based tutorial to understand more about that. So here your processing master is basically breaking down the application into tasks. What it does internally is once your application is submitted, your application to be run on Yarn processing framework is handled by resource manager. Now forget about the Yarn part as of now. I mean, who does the negotiating of resources, who allocates them, how does the processing happen on the nodes, right? So that's all to do with how Yarn handles the processing request. So you have your data which is stored in SDFS, broken down into one or multiple splits. Depending on the input format which has been specified by the developer, your input splits are to be worked upon by your one or multiple map tasks which will be running within the container on the nodes. Basically you have the resources which are being utilized. So for each map task you would have some amount of RAM which will be utilized, and then further the same data which has to go through reducing phase, that is your reduce task, will also be utilizing some RAM and CPU cores. Now internally you have these functions which take care of deciding on number of reducers, doing a mini reduce, and basically reading and processing the data from multiple data nodes. Now this is how your MapReduce programming model makes parallel processing work, or processes your data which is stored across multiple machines. Finally, you have your output which is getting stored on SDFS. So let's have a quick demo on MapReduce and see how it works on a Hadoop cluster. Now we have discussed briefly about MapReduce, which contains mainly two phases, that is your mapping phase and your reducing phase. And mapping phase is taken care by your mapper function, and your reducing phase is taken care by your reducer function. Now in between we also have sorting and shuffling, and then you have other phases which is partitioner and combiner, and we will discuss about all those in detail in later sessions. But let's have a quick demo on how we can run a MapReduce which is already existing as a package jar file within your Apache Hadoop cluster or even in your Cloudera cluster. Now we can build our own MapReduce programs. We can package them as jar, transfer them to the cluster, and then run it on a Hadoop cluster on Yarn, or we could be using already provided default programs. So let's see where they are. Now these are my two machines which I have brought up, and basically this would have my Apache Hadoop cluster running. Now we can just do a simple start -all.sh. Now I know that this script is deprecated and it says instead use start DFS and start Yarn, but then it will still take care of starting of my cluster on these two nodes, where I would have one single name node, two data nodes, one secondary name node, one resource manager, and two node managers. Now if you have any doubt in how this cluster came up, you can always look at the previous sessions where we had a walkthrough in setting up a cluster on Apache, and then you could also have your cluster running using less than 3 GB of your total machine RAM, and you could have an Apache cluster running on your machine. Now once this cluster comes up, we will also have a look at the web UI which is available for name node and resource manager. Now based on the settings what we have given, our UIs will show us details of our cluster, but remember the UI is only to browse. Now here my cluster has come up. I can just do a JPS to look at Java related processes, and that will show me what are the processes which are running on C1, which is your data node, resource manager, node manager, and name node. And on my M1 machine, which is my second machine which I've configured here, I can always do a JPS, and that shows me the processes running, which also means that my cluster is up with two data nodes with two node managers. And here I can have a look at my web UI. So I can just do a refresh, and the same thing with this one, just do a refresh. So I had already opened the web pages. So you can always access the web UI using your name node's host name and 570 port. It tells me what is my cluster ID, what is my block pool ID. It gives you information of what is the space usage, how many live nodes you have, and you can even browse your file system. So I have put in a lot of data here. I can click on browse the file system, and this basically shows me multiple directories, and these directories have one or multiple files which we will use for our MapReduce example. Now if you see here, these are my directories which have some sample files, although these files are very small, like 8.7 kilobytes. If you look into this directory, if you look into this, I have just pulled in some of my Hadoop logs and I have put it on my SDFS. These are a little bigger files, and then we also have some other data which we can see here, and this is data which I've downloaded from web. Now we can either run a MapReduce on a single file or in a directory which contains multiple files. Let's look at that. Before looking a demo on MapReduce, also remember MapReduce will create a output directory, and we need to have that directory created. Plus we need to have the permissions to run the MapReduce job. So by default, since I'm running it using admin ID, I should not have any problem. But then if you intend to run MapReduce with a different user, then obviously you will have to ask the admin, or you will have to give the user permission to read and write from SDFS. So this is the directory which I've created, which will contain my output once the MapReduce job finishes. And this is my cluster file system. If you look on this UI, this shows me about my yarn which is available for taking care of any processing. It as of now shows that I have total of 8 GB memory and I have 8 vCores. Now that can be depending on what configuration we have set or how many nodes are available. We can look at nodes which are available, and that shows me I have 2 node managers running. Each has 8 GB memory and 8 vCores. Now that's not true actually, but then we have not set the configurations for node managers, and that's why it takes the default properties, that is 8 GB RAM and 8 vCores. Now this is my yarn UI. We can also look at scheduler, which basically shows me the different queues if they have been configured, where you will have to run the jobs. We'll discuss about all these in later in detail. Now let's go back to our terminal and let's see where we can find some sample applications which we can run on the cluster. So once I go to the terminal, I can, well, submit the MapReduce job from any terminal. Now here I know that my Hadoop related directory is here, and within Hadoop you have various directories. We have discussed that in binaries you have the commands which you can run. In sbin you basically have the startup scripts, and here you also notice there is a share directory in the end. If you look in the share directory, you would find Hadoop, and within Hadoop you have various subdirectories in which we will look for MapReduce. Now this MapReduce directory has some sample jar files which we can use to run a MapReduce on the cluster. Similarly, if you are working on a Cloudera cluster, you would have to go into opt Cloudera parcel cdh/lib, and in that you would have directories for SDFS MapReduce or SDFS yarn, where you can still find the same jars. It is basically a package which contains your multiple applications. Now how do we run a MapReduce? We can just type in Hadoop and hit enter, and that shows me that I have an option called jar which can be used to run a jar file. Now at any point of time, if you would want to see what are the different classes which are available in a particular jar, you could always do a jar minus xvf. For example, I could say jar xvf, and I could say user local Hadoop share Hadoop MapReduce, and then list down your jar file. So I'll say Hadoop MapReduce examples, and if I do this, this should basically unpack it to show me what classes are available within this particular jar. And it has done this. It has created a meta file and it has created a org directory. We can see that by doing a ls, and here if you look in ls org, since I ran the command from a home directory, I can look into org Apache Hadoop examples, which shows me the classes which I have and those classes contain which mapper or reducer classes. So it might not be just mapper and reducer, but you can always have a look. So for example, I am targeting to use word count program, which does a word count on files and gives me a list of words and how many times they occur in a particular file or in set of files. And this shows me that what are the classes which belong to word count. So we have a int sum reducer. So this is my reducer class. I have tokenizer mapper, that is my mapper class, right? And basically this is what is used. These classes are used if you run a word count. Now there are many other programs which are part of this jar file, and we can expand and see that. So I can say Hadoop jar and give your path. So I'll say Hadoop jar user local Hadoop share Hadoop MapReduce examples, and if I hit on enter, that will show me what are the inbuilt classes which are already available. Now these are certain things which we can use. Now there are other jar files also. For example, I can look at Hadoop, and here we can look at the jar files which we have in this particular path. So this is one Hadoop MapReduce examples which you can use. You can always look in other jar files, like you can look for Hadoop MapReduce client, job client, and then you can look at the tests one. So that is also an interesting one. So you can always look into Hadoop MapReduce client, job client, and then you have something ending with tests. So if I would have tried this one using my Hadoop jar command, so in my previous example, when we did this, it was showing me all the classes which are available, and that already has a word count. Now there are other good programs which you can try, like TerraGen to generate dummy data, TerraSort to check your sorting performance, and so on, and TerraValidate to validate the results. Similarly, we can also do a Hadoop jar, as I said, on Hadoop MapReduce. I think that was client, and then we have job client, and then test jar. Now this has a lot of other classes which can be used, or programs which can be used for doing a stress testing or checking your cluster status and so on. One of them, interesting one, is testdfsio. But let's not get into all the details in first instance. Let's see how we can run a MapReduce. Now if I would want to run a MapReduce, I need to give Hadoop jar and then my jar file, and if I hit on enter, it would say it needs the input and output. It needs which class you want to run. So for example, I would say word count, and again if I hit on enter, it tells me that you need to give me some input and output to process. And obviously this processing will be happening on cluster, that is our yarn processing framework, unless and until you would want to run this job in a local mode. So there is a possibility that you can run the job in a local mode, but let's first try how it runs on the cluster. So how do we do that? Now here I can do a hdfs ls slash command to see what I have on my SDFS. Now through my UI, I was already showing you that we have set of files and directories which we can use to process. Now we can take up one single file. So for example, if I pick up new data, and I can look into the files here, what we have, and we can basically run a MapReduce on a single file or multiple files. So let's take this file, whatever that contains, and I would like to do a word count so that I get a list of words and their occurrence in this file. So let me just copy this. Now I also need my output to be written, and that will be written here. So here, if I want to run a MapReduce, I can say Hadoop, which we can pull out from history. So Hadoop jar word count. Now I need to give my input, so that will be new data, and then I will give this file which we just copied. Now I'm going to run the word count only on a single file, and I will basically have my output which will be stored in this directory, the directory which I have created already, mr output. So let's do this output, and this is fair enough. Now you can give many other properties. You can specify how many map jobs you want to run, how many reduce jobs you want to run. Do you want your output to be compressed? Do you want your output to be merged? or many other properties can be defined when you are specifying word count, and then you can pass in an argument to pass properties from the command line which will affect your output. Now once I go ahead and submit this is basically running a simple inbuilt MapReduce job on our Hadoop cluster. Now obviously internally it will be looking for name node. Now we have some issue here and it says the output already exists. What does that mean? So it basically means that Hadoop will create an output for you. You just need to give a name, but then you don't need to create it. So let's append the output with number 1, and then let's go ahead and run this. So I've submitted this command. Now this can also be run in background if you would want to run multiple jobs on your cluster at the same time. So it takes total input paths to process is 1. So that is, there is only one split on which your job has to work. Now it will internally try to contact your resource manager, and basically this is done. So here we can have a look and we can see some counters here. Now what I also see is for some property which it is missing, it has run the job, but it has run in a local mode. It has run in a local mode. So although we have submitted, so this might be related to my yarn settings, and we can check that. So if I do a refresh, when I have run my application, it has completed. It would have created an output, but the only thing is it did not interact with your yarn. It did not interact with your resource manager. We can check those properties, and here if we look into the job, it basically tells me that it went for mapping and reducing. It would have created an output. It worked on my file, but then it ran in a local mode. It ran in a local mode. So MapReduce, remember, is a programming model, right? Now, if you run it on Yarn, you get the facilities of running it on a cluster where Yarn takes care of resource management. If you don't run it on Yarn and run it on a local mode, it will use your machine's RAM and CPU cores for processing. But then we can quickly look at the output, and then we can also try running this on Yarn. So if I look into my HDFS and if I look into my output, MR output, that's the directory which was not used actually. Let's look into the other directory which is ending with 1, and that should show me the output created by this MapReduce. Although it ran in a local mode, it fetched an input file from your SDFS and it would have created output in SDFS. Now that's my part file which is created, and if you look at part minus R minus these zeros, if you would have more than one reducer running, then you would have multiple such files created. We can look into this. What does this file contain? Which should have my word count, and here I can say cat, which basically shows me what is the output created by my MapReduce. Let's have a look into this. So the file which we gave for processing has been broken down, and now we have the list of words which occur in the file plus a count of those words. So if there is some word which is more, then it shows me the count. So this is a list of my words and the count for that. So this is how we run a sample MapReduce job. I will also show you how we can run it on Yarn. Now let's run MapReduce on Yarn, and initially when we tried running a MapReduce, it did not hit Yarn, but it ran in a local mode, and that was because there was a property which had to be changed in MapReduce-site file. So basically if you look into this file, the error was that I had given a property which says mapred.framework.name, and that was not the right property name, and it was ignored, and that's why it ran in a local mode. So I changed the property to mapreduce.framework.name, restarted my cluster, and everything should be fine now, and that mapred-site file has also been copied across the nodes. Now to run a MapReduce on a Hadoop cluster so that it uses Yarn, and Yarn takes care of resource allocation on one or multiple machines. So I'm just changing the output here, and now I will submit this job, which should first connect to the resource manager. And if it connects to the resource manager, that means our job will be run using Yarn on the cluster rather than in a local mode. So now we have to wait for this application to internally connect to resource manager, and once it starts there, we can always go back to the web UI and check if our application has reached Yarn. So it shows me that there is one input part to be processed. That's my job ID, that's my application ID, which you can even monitor status from the command line. Now here the job has been submitted, so let's go back here and just do a refresh on my Yarn UI, which should show me the new application which is submitted. It tells me that it is in accepted state. Application master has already started, and if you click on this link, it will also give you more details of how many map and reduce tasks would run. So as of now, it says the application master is running. It would be using this node, which is M1. We can always look into the logs. We can see that there is a one task attempt which is being made. And now if I go back to my terminal, I will see that it is waiting to get some resources from the cluster. And once it gets the resources, it will first start with the mapping phase, where the mapper function runs. It does the map tasks, one or multiple depending on the splits. So right now we have one file and one split, so we will have just one map task running. And once the mapping phase completes, then it will get into reducing, which will finally give me my output. So we can be toggling through these sessions. So here I can just do a refresh to see what is happening with my application. Is it proceeding? Is it still waiting for resource manager to allocate some resources? Now, just a couple of minutes back, I tested this application on Yarn, and we can see that my first application completed successfully. And here we will have to give some time so that Yarn can allocate the resources. Now, if the resources were used by some other application, they will have to be freed up. Now, internally, Yarn takes care of all that, which we will learn more detail in Yarn, or you might have already followed the Yarn based session. Now here we will have to just give it some more time, and let's see if my application proceeds with the resources what Yarn can allocate to it. Sometimes you can also see a slowness in what web UI shows up, and that can be related to the amount of memory you have allocated to your nodes. Now for Apache, we can have less amount of memory and we can still run the cluster. And as I said, the memory which shows up here, 16 GB and 16 cores, is not the true one. Those are the default settings, right? But then my Yarn should be able to facilitate running of this application. Let's just give it a couple of seconds and then let's look into the output here. Again, I had to make some changes in the settings because our application was not getting enough resources, and then basically I restarted my cluster. Now let's submit the application again to the cluster, which first should contact the resource manager, and then basically the map and reduce process should start. So here I've submitted an application. It is connecting to the resource manager, and then basically it will start internally an app master, that is application master. It is looking for the number of splits, which is 1. It's getting the application ID, and it basically then starts running the job. It also gives you a tracking URL to look at the output. And now we should go back and look at our Yarn UI if our application shows up here, and we will have to give it a couple of seconds when it can get the final status change to running, and that's where my application will be getting resources. Now if you closely notice here, I have allocated specific amount of memory, that is 1.5 GB for node manager on every node, and I have basically given 2 cores each, which my machines also have, and my Yarn should be utilizing these resources rather than going for default. Now the application has started moving, and we can see the progress bar here, which basically will show what is happening. And if we go back to the terminal, it will show that first it went in deciding map and reduce. It goes for map. Once the mapping phase completes, then the reducing phase will come into existence, and here my job has completed. So now it has basically used, we can always look at how many map and reduce tasks were run. It shows me that there was one map and one reduce task. Now with the number of map tasks depends on the number of splits, and we had just one file which is less than 128 MB, so that was one split to be processed, and reduce task is internally decided by the reducer, or depending on what kind of property has been set in Hadoop config files. Now it also tells me how many input records were read, which basically means these were the number of lines in the file. It tells me output records, which gives me the number of total words in the file. Now there might be duplicates, and that which is processed by internal combiner further processing or forwarding that information to reducer, and basically reducer works on 335 records, gives us a list of words and their count. Now if I do a refresh here, this would obviously show my application is completed. It says succeeded. You can always click on the application to look for more information. It tells me where it ran. Now we do not have a history server running as of now, otherwise we can always access more information. So this leads to history server where all your applications are stored. But I can click on this attempt tasks, and this will basically show me the history URL, or you can always look into the logs. So this is how you can submit a sample application which is inbuilt, which is available in the jar on your Hadoop cluster, and that will utilize your cluster to run. Now you could always, as I said, when you're running a particular job, remember to change the output directory, and if you would not want it to be processing a single individual file, you could also point it to a directory. That basically means it will have multiple files, and depending on the file sizes there would be multiple splits, and according to that multiple map tasks will be selected. So if I click on this would submit my second application to the cluster, which should first connect to resource manager. Then resource manager has to start an application master. Now here we are targeting 10 splits. Now you have to sometimes give a couple of seconds in your machines so that the resources which were used are internally already freed up, so that your cluster can pick it up and then your yarn can take care of resources. So right now my application is in undefined status, but then as soon as my yarn provides it the resources, we will have the application running on our yarn cluster. So it has already started. If you see, it is going further. Then it would launch 10 map tasks, and the number of reduced tasks would be decided on either the way your data is or based on the properties which have been set at your cluster level. Let's just do a quick refresh here on my yarn UI to show me the progress. Also take care that when you are submitting your application, you need to have the output directory mentioned. However, do not create it. Hadoop will create that for you. Now, this is how you run a MapReduce without specifying properties, but then you can specify more properties. You can look into what are the things which can be changed for your mapper and reducer, or basically having a combiner class which can do a mini reducing, and all those things can be done. So we will learn about that in the later sessions. Thank you and keep learning.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.